Hello, I'm Yongjin Jo of Rehabilitation Biomechatronics Lab. I'll talk about the TOM project proposal. The thesis is Soft Exosuit System for Ankle Assistance. Soyeon Moon and I will do this project together. First, I'll explain the background and goal of our project. Then current system will be briefly explained. After that, key tasks will be presented. Last, I'll talk about evaluation method. The number of people suffering from gait disorder is increasing due to the aging of population and the increase in the number of patients with neurological disorders. Therefore, demands for robot technologies that can assist rehabilitation is increasing. However, exoskeletons normally used for gait assistance have several disadvantages. They are heavy and difficult to wear, making it difficult to guarantee patient convenience. Also, because it consists of rigid metal, when the joint misalignment between exoskeleton and wearer happens, the wearer can be hurt. To improve natural gait assistance, we will develop the soft exosuit system in the form of clothing. As the suit is made by fabrics, it can offer more comfortable working environment to wearers. So in this project, we will do ankle assistant control for patients to work more naturally using soft exosuit systems. In this slide, I briefly explain current exosuit hardware system. The overall system can be divided as actuation unit and textile suit. First, I'll explain actuation unit. You can see two pictures on the right. This is the cable-driven actuation unit. The pulley is connected to motor shaft. When the motor rotates, cable length changes, so we can assist vertical force to wearers. Power transmission is occurred with Bowden cables. This is consists of inner cable and outer housing. When the motor rotates, only inner cable moves along the outer cable, so it can reduce friction. Using two actuation units, we will assist dorsiflexion motion and plantar flexion motion. Next part is textile suit. At the cuff, the textile suit is worn. Textile suit is for holding the body to prevent chafing, so we can reduce the loss of power. Also, it can hold the cable's path. As you can see the video, when the cable moves, it raises the heel or toes, so we can assist both motion. By assisting plantar flexion motion, wearer can get extra power for moving forward. Dorsiflexion assistance is important to neurological disorder patients because their main symptom is foot drop. We can handle this symptom by assisting dorsiflexion motion. Our lab recently has set up the hardware system. To achieve our goal, we need to control this system. The overall system is represented at the slide. Controller is composed of two parts. High-level controller decides revised desired gait trajectory. It detects key events of gait cycle based on foot IMU measurements and generates desired gait trajectory based on gait events and cable force measurement from road cell sensors. The low-level controller runs closed-loop control on motor position for the actuation system to track desired trajectory generated by high-level controller. To evaluate this controller, we have several subtests. Now I'll explain this. First, we need to detect people's gait cycle. To assist each patient's walking, we need to find out the characteristics of their own gait because those are all different per person. Total time of gait is all different and the time of each phase is also different. Especially in case of patients, the deviation becomes very large due to after effects of disorders. Therefore, it is necessary to understand what the wearer's gait characteristics are. To find out them, we will use IMU sensors. IMU is a sensor which can measure angle, force, and velocity. By measuring ankle joint angle and angular velocity, we will find timing of toe-off and mid-swing. Therefore, we can find out the time of gait cycle and the phase of gait. Gait cycle is segmented to three phases. Phase 1 means stance phase, and phase 2 means heel strike to pre-swing stage. And then phase 3 means swing phase to weight acceptance. We will control the position of cable using the data of Forcera. The calculation methods for plantar flexion and dorsiflexion are different. Plantar flexion cable trajectory generation algorithm was implemented to consistently deliver plantar flexion force to ankle at appropriate timing. Main goal is to generate plantar flexion force that has onset at the end of mid-stance, reaches a desired peak force, and diminishes before beginning of swing phase. The cable displacement is quite large, so the transition time from slack state to tension state takes a while. So we need to calculate about the velocity too. And then we can revise the base cable position. A similar algorithm is used for dorsiflexion cable trajectory generation algorithm. When we generate the dorsiflexion trajectory, only calculating about displacement is enough. The system modeling for calculation is not done yet. We will keep doing the rest. Among the sub-tasks, I'll charge the trajectory generation, and Sohyun, my colleague, will charge IMU-based gait detection. As mentioned before, it is not possible to test with person because of IRB permission issue. Therefore, we will use a test apparatus. The test apparatus is shown at the slide, and its shape is like a shoes and rotate along a single axis. Therefore, it can mimic the sagittal movement of foot. Using this, we will measure the overall force error rate to evaluate the control level. Also, we will measure the angle movement of apparatus. Through this, we can decide whether the assistant from soft exosuit can make proper ankle movement. With these two kinds of experiments, we will evaluate the feasibility of ankle assistance with soft exosuit system. This is the end of the presentation. Thank you for listening.